For this problem, you're going to have to calculate the energy of the photon emitted when an electron in the hydrogen atom falls from your initial state of n equals to 5 to your final state of n equals to 2. And this problem clues you in that you're supposed to use the Bohr equation to solve it. So knowing this, here is the Bohr equation. And if I plug in for my n final and n initial, I can solve for my change in energy, which is negative 4.573 times 10 to the negative 19 joules. And because we're asked to find the energy of a photon, we don't necessarily need the negative sign here because that just indicates that energy is being emitted. So our energy of photon is just 4.57 times 10 to the negative 19 joules. So that's part one. And for part two, you're supposed to calculate the wavelength of light emitted for the n equals 6 to n equals to 3 transition. And again, using the Bohr equation, we can plug in what our n final and n initial are, which I've done here. And I get a value of negative 1.815 times 10 to the negative 19 joules. And now we have to figure out a way to convert this energy into wavelength, which we're being asked to find. So I know I have this equation here where energy equals to h nu, but lambda doesn't appear here in this equation, so I have to figure out another equation I can use where lambda does appear in. So I have c equals to h nu, and if I rewrite it, I get nu equals to c over lambda. And if I combine both of these equations, I can have energy and lambda in the same equation. So if I plug in my numbers for energy, and I know h is Planck's constant, and c is the speed of light, which is also constant, I can solve for lambda. And if I do the calculations up, I get lambda equals to 1.094 times 10 to the negative 6 joules.